Hi, my name is Andrew Foss, and I'll be showing you my Turn-in 3 problems. So first, my first problem asks for a general conduction equation derivation within cylindrical coordinates. This is then solved for using initial and boundary conditions to find the interior surface temperature. Next, using this interior surface temperature, vapor condensation rate is found across the cylindrical car, and then finally, the warm ocean air begins to convectively heat the car, and we're tasked with finding the temperature at a specific location at a specific time. And so this problem addresses conduction equation boundary conditions, or conduction equation deriving, solving, uses this cylindrical coordinate system, and solves for transient heat transfer as well as condensation. So in my solution to this problem, first I set up the temperature profile as well as a system diagram. I started my conduction equation derivation with an energy balance, which then formed into a differential version based upon the cylindrical slice seen here. Next, once this equation was completely solved for with a volumetric slice canceled out on almost on every term. This then led us to finding the internal temperature, surface temperature. To do this, we use the boundary conditions, the first of which is the temperature of the exterior surface, and the second of which is the boundary flux condition. Using these, our differential equation, which we had simplified, was then integrated and then solved for at the inner radius for the interior surface temperature. To find the mass condensation rate, this properties were gathered at the saturation temperature. Then the modified latent heat of vaporization was found, and then subsequently the heat transfer was found. This then led us to use these two values to find the total mass transfer, which is rather high. However, condensation, when found dropwise, is highly unsteady, and a steady state model over a long period of time perhaps is very inaccurate. Next, the temperature at the given time at this position here was found for by doing a 2D transient heat transfer analysis, in which we examined our car as a short cylinder, which involved the analyses of a wall and a cylinder model, long cylinder model. These were then, Biot numbers were found, which helped us find our values, and then these were then solved for, leading to our expression for change in temperature, which was then solved, and then time was then found to be a little over 3 hours. For my next problem, oxygen was purified for medical grade oxygen tanks. The first part of this problem asks for the the asks for a solution to the steady state mass transfer within this unit op. And then in the second part, we look at a transient, smaller scale membrane flux. So for part one, this separator was modeled as so, with the retentate and the permeate being separated. So we were tasked with finding the area for this separator, which was done by finding the flux via the driving force and the permeance. The driving force was a log mean pressure gradient, and the permeance was a given value. So once we had this flux, we could determine the area by analyzing the outlet permeate stream. This then led to our transient analysis, in which we found the moles fluxing at the given time of 30 seconds by using Fick's law, further deriving it, separating, and then integrating. My third problem dealt with starlight on an asteroid. In this problem, radiative heat transfer heats an asteroid deep in space. However, this asteroid also emits heat such that a steady state surface temperature could be found. So we were tasked with finding this surface temperature, which we did by analyzing the convective or radiative heat transfer around the system. So the radiative transfer in must equal the radiative transfer out. From here, the surface temperature could be found. And then using cylindrical coordinates, the conduction equation was then simplified and then integrated twice using a symmetry boundary condition and an initial condition to find our function of temperature. My last problem dealt with hot pipes within an apartment. The first question asks us to compare natural and forced external heat flow over the pipes. And the second part of the question asks for us to examine the internal convection of the system. So starting off, we compared external and natural convection, with natural convection going first. Rayleigh's number was found, which then led us to the Newsett number, which then helped us find our heat transfer coefficient, and eventually our heat transfer of 582 watts. For forced external convection, Reynolds number was found, and then the Newsett number for that laminar flow was then found, and then the convective heat transfer coefficient was found, and then ultimately the heat transfer was found. And as you can see, when fanning the pipes, four times as much heat transfer is acquired. So it's a very good thing. And now, lastly, for our internal forced convection, we first assumed steady state and a fully hydrodynamically and thermally developed pipe. From an average temperature between the surface temperature and the initial temperature was found. From there, we gathered our properties, and we found our Reynolds number, our Newsett number, and our exiting temperature, which didn't vary very much. So yeah, thank you.